So if you believe the mainstream headlines out there, quantum computers are, well, just about ready to solve every single problem known to humanity by tomorrow afternoon, right? We're told they're going to crack every password on Earth, magically cure every disease, and hey, maybe even fold your laundry while they're at it. But here's the uncomfortable truth. Most explanations of quantum computing that you read online, they are fundamentally wrong. They rely on mystical analogies about parallel universes or magic coins that are somehow both heads and tails at the exact same time. So today, our mission in this explainer is to completely separate that magical hype from the actual, ground-up physics.
Hello, I am Mr. Shaw, and you are watching Mr. Shaw Explains Tech. Listen, today we're going to entirely strip away the marketing hype. If you want a bedtime story about the multiverse, you might want to turn back now. But if you actually want to understand what quantum computing is at a physical level, why it's so painfully difficult to build, and what problems it's legitimately designed to solve, well, you are in the exact right place. Okay, let's dive right into this. Here's our structural journey for today's explainer. We're going to cover bits versus qubits, entanglement and interference, specialized applications, the decoherence problem, and finally, the realistic horizon.
Section 1. Bits versus qubits, escaping the both at the same time myth. To truly understand a quantum computer, we really have to start by looking at the machine you're using to watch this explainer right now. Your smartphone, your laptop, the massive cloud servers hosting all this data, they all run on classical bits. Now, a bit is simply a switch. It's definitively either a 0 or a 1. That's it. Everything you do digitally, every single video frame, every text message, every complex calculation is literally just billions of these zeros and ones being flipped and combined at blinding speeds. A quantum computer, though, entirely replaces that classical bit with a qubit, or quantum bit.
Now, what's really interesting about this contrast is how fundamentally different these two foundations of computing actually are. On one hand, we have the simple, definitive 0 or 1 of classical bits. But on the other hand, we have the qubit, which exists as a linear combination of states in a probability space. The really common, pervasive myth here is that a qubit can be a 0 and a 1 at the exact same time, which, of course, leads people to think it magically tries every single possible answer simultaneously, like some kind of omnipotent supercomputer. Honestly, that is definitively wrong. What a qubit actually does is exist in a superposition of states.
Let's lock down what that actually means. Superposition is a quantum state where a qubit exists as a probability of being measured as a 0 or a 1. Before you measure it, it isn't both 0 and 1. Think of it like a spinning coin on a table. While that coin is actively spinning, is it heads or is it tails? Well, actually, it's neither. It's just a blur of motion, right? It's existing in a probability space. But the moment you slap your hand down on the table, the moment you measure or read that qubit, it forces it to collapse into a definitive 0 or 1. So superposition definitely doesn't mean doing infinite things at once.
Section 2. Entanglement and interference, the secret sauce. Because here is the reality. If superposition were the only trick up our sleeve, quantum computers wouldn't be worth their multi-billion-dollar price tags. I mean, operating in a probability space is cool and all, but the real transformative computational power comes from two other mind-bending quantum mechanical phenomena.
The first of these is entanglement. Entanglement occurs when two or more qubits become inextricably linked together. If you change the state of one entangled qubit, the state of the other changes instantly, regardless of the physical distance between them. Albert Einstein famously couldn't stand this idea. He called it spooky action at a distance. But in a quantum processor, this phenomenon is absolutely crucial because it allows qubits to share a completely unified state.
And this brilliantly illustrates the true mathematical power of the whole system. Because qubits can share that unified state through entanglement, when you add qubits to an entangled system, the computational capacity doesn't just add up linearly, like 1 plus 1 plus 1. Instead, it scales exponentially. It grows at a rate of 2 to the power of n, where n is the number of qubits. This exponential scaling is exactly what gives quantum computers their theoretical dominance over classical machines. But as you'll see, scaling that up physically is literally an engineering nightmare, which brings us to how we actually get answers out of this system in the first place.
You see, quantum algorithms are not designed to just spit out a single magical correct answer on the first try. Instead, you have to use interference. You design algorithms using constructive and destructive interference. It's very much like visualizing ripples on a pond of water. You engineer the probabilities so that the ripples of the incorrect answers destructively cancel each other out, and the ripples of the correct answer are constructively amplified when you finally measure the system. If you fail to manage this interference properly, well, All those probabilities just collapse into useless random noise.
Section 3, specialized applications. What are they actually good for? Because of exactly how those algorithms and probabilities work, I need to make this crystal clear. Quantum computers are specialized accelerators. They are not just faster versions of your laptop. They will never render your videos faster, they won't give you zero-lag web browsing, and no, they definitely won't run your video games better. For most basic everyday tasks, a classical computer is vastly superior and, frankly, far more reliable.
So, the crucial point is understanding where quantum computers actually excel. First up, molecular simulation. Classical computers struggle terribly to model the interactions of even small molecules, simply because the quantum states of electrons scale exponentially. But a quantum computer, it operates using those exact same quantum rules natively. That makes it a perfect tool for designing new pharmaceuticals or better battery catalysts. Second, optimization problems. We're talking about finding the absolute best mathematical solution out of millions of variables for things like global logistics or financial risk modeling. And finally, cryptography. Now this is the scary one. Classical computers are extremely slow at prime factorization, but Shor's algorithm, running on a powerful enough quantum computer, could theoretically break the security backbone of the modern internet by easily cracking RSA public key encryption.
Which naturally leads us to Section 4, the decoherence problem. Why don't we all have one? If the math for things like Shor's algorithm works perfectly on paper, we really have to ask the obvious question. Why isn't every tech company finished building these machines? Why don't we all have one sitting on our desks? Well, the answer is that the main bottleneck isn't software, it's physics. Beat the primary engineering villain of our explainer today, decoherence. Qubits are incredibly, almost unimaginably hypersensitive. Decoherence is the collapse of that fragile quantum state into a normal classical state due to a slight outside disturbance. Think about it this way. If a qubit is hit by a stray magnetic field, a microscopic change in temperature, or literally even a single stray photon of light, it collapses. The whole calculation is instantly ruined.
Let's look at how we tackle this, because to fight this decoherence, scientists have to go to excruciating engineering lengths. Step 1, you have to house these qubits inside massive dilution refrigerators. We're talking cool to fractions of a degree above absolute zero. These environments are literally colder than deep space. Step 2, because errors still happen constantly even in that extreme cold, you have to implement massive quantum error correction protocols. And step 3, all this overhead means you need to combine thousands of physical, noisy qubits just to construct a single, stable, error-corrected, logical qubit that you can actually trust.
And that brings us squarely into our current reality. We are currently living in the NISQ era, which stands for Noisy Intermediate Scale Quantum. What this actually means is that, right now, humanity only has machines with dozens to hundreds of qubits. And because they are so noisy, they simply make far too many errors to run the deep, transformative calculations, like Shor's algorithm that we discussed earlier. The hardware just isn't there yet.
And that brings us to Section 5, the realistic horizon, engineering over magic. I want to reinforce something here. Building these machines is not just a software update. It is arguably the most difficult hardware engineering undertaking in human history. So, let's summarize the core takeaways from our explainer today. Quantum computing is totally real. And yes, it is mathematically sound, but it is not magic. It requires excruciatingly precise control of subatomic states inside giant high-tech freezers. As we established, it will never replace the smartphone in your pocket. But over the coming decades, as we slowly conquer the physics of decoherence, it will steadily transform material science, drug discovery, and cryptography. The bottom line you should take away from all this is simple. Stop looking for sci-fi miracles and start watching for the steady, incredibly hard-won engineering milestones. If you found this breakdown intellectually honest and helpful in cutting through all that noise, make sure to hit that subscribe button. And I want to hear from you. Which quantum myth do you want me to violently dismantle next? Let me know down in the comments, keep your curiosity sharp, and I will see you in the next explainer.